And today I will talk about this topic, which is AI-assisted routing. So this is the outline of my talk, and I will focus on talking to scenarios to show how AI may be able to help us to do routing in a significant way. So we all know that routing is one of the most complicated and time-consuming steps in physical design, and is usually the runtime bottleneck because there are many complex objectives to achieve, and also there will be many nets fighting for the same routing resources. But nowadays, we can see a lot of advance in AI, and we would like to see whether AI can help us to do routing. So there have been works on doing AI for routing. For example, a few years back, we had reinforcement learning to connect to PNet, and then reinforcement learning to generate our SMT from our group, and then also RL to determine the net order or to add Steiner point. And finally, last year from our group, we have this diffusion model to do global routing. So we can see that we are gradually moving towards a more practical goal from one 2P-net to one single multi-P-net to now routing all the nets in the global routing. But still, global routing is not the, okay. So, and also accumulating these experiences, telling us that it may not be good to use AI to generate a complete routing solution, because there will be a lot of issues like open or some dangling part. So it will be hard for the AI model to generate a complete clean routing solution. But rather, it will be good if we can use AI to generate some guidance for the corresponding EDA tools for the routers. So here are some of the schemes that we have used. So instead of using AI to generate the routing solution, we would like to have an AI agent to learn to generate some prior knowledge that can be used by the router. And then we tried that different scheme. Some of them will do supervised learning, and then some of them will do reinforcement learning. And after the training, then we only use AI agent to generate prior knowledge, and the prior knowledge will be used by the corresponding EDA tools to perform the job. So today we will look at two scenarios. One is construction of a shallow light tree, and the other one is routing of multiple nets in a window. So for the first scenario is the construction of shallow light tree. So we all know that shallow light tree is very important because on one hand, we want to minimize the path, which implies wide delay. We also want to minimize the total weight of the tree that correspond to routing resources, power consumption, and also to delay. So usually, considering the total weight of the tree, we would like to have a RSMT, rectilinear Steiner minimum tree, which has the lightest weight, total weight. And considering the path from the source to each of the pin, we'll consider the RSMA, the rectilinear Steiner minimum of a resin tree, in which all the connections from the root to the pin is the shortest possible. So we are seeing how these two can be generated and combined with AI. So here in our work, we will use Float and CL to approximate the RSMT and the RSMA. So one more thing to introduce is about two parameters. One is to measure the shallowness. It is the maximum among all the vertices V except the root. this ratio, which is the path length from the root to this node to the Manhattan distance from the root to this node. So this is a ratio bigger than 1, and we take the maximum. This is the alpha. And then the other one is the beta, which measure the lightness of the tree. So this is the total weight of the tree divided by the weight of the RSMT. So again, this is bigger than 1, and this showing how far it is from the optimal solution. So for the shell-like tree construction, some of the work, they will have a limited alpha, and they minimize the beta, or they have a limited beta and minimize the alpha. Okay. So the intuition of this work is we want to use the AI approach to detect, like usually after you connect all the point with our SMT, some of the point will violate the constraint, the delay constraint, and then we need to reconnect them. But here we would like to use the AI to predict which are those points. So we are going to build a model to achieve this. After we predict the point, we will connect this point with the our SMA, and then now we have an our SMA and our SMT, and then we will combine the two to form a shallow-like tree. Okay. So in order to predict the set of points, we call them the critical set. We'll use the following model. So first of all, given the set of pin, we will construct the RSMT, and this RSMT and the pin will be encoded into embeddings, and then feed into a pointer network. So this pointer network is the one we built for a previous work that construct the RSMT. Okay, so this pointer network will will output a sequence of pins, and then we will construct the tree according to the pins. But here we are making use of this pointer network to also output a sequence of pins, but the output will help us to identify the critical set. So the rule is like this. So for example, we generate a sequence of pins like this, 1, 2, 3, 4, 5, 6, 7, until 10. And those which is generated before the root, okay, will be taken as the critical set. So for this example, this 1, 2, 3, 4 will be in the critical set. Okay. So this is our more detailed model. So you can, as what I explained, given the pin, we construct the RSMT, and then it will go through our model and generate a critical set. And then the critical set will combine with the RSMT using the approach similar to in SORT and produce the shallow-like tree. And this result, we will compute the alpha beta, and the result can be used to reward the model, to train the model. Okay. So by doing that, here is the result that we can see how much we can improve over the SORT. So on this side, you can see we use a different data set from small to huge to large, and then this is different alpha, and then this is the beta. So we can see that the beta is smaller the better, and you can see that for all the scenario with the AI approach can improve over the SORT. And here are some of the output. So this is the RSMT, and this is corresponding result produced by SORT without this AI model. And this is the one with the AI model. You can see for some of the cases, it's pretty obvious a good improvement. Okay. So another scenario is another interesting problem, which is about routing of multiple nodes in a window. Okay. So this usually we'll use maze routing sequential, and then we'll rip up and reroute. So this is the most common way to do, because if we want to simultaneously route all the net, it will we either formulate as a network fault problem, IOP problem, but it will take a long time. So in the following work, we would like to see whether we can use some AI approach to help to route the net to a certain extent simultaneously. Okay, so some intuition is here. So suppose we have 3 net. If we do use sequential approach, we need to rip up and reroute several times, several nets before we can come up with a feasible solution. While the feasible solution may be something like this. So we would like to use AI to learn this guide for the net. So they will be considering the path of other nets in order to generate a guide for the nets for each individual net. Okay. So so this is the so this will be the model that the target that we would like to have. So imagine a window, 3-dimensional window, and then there are pseudo pin, there are real pin, and then we have this global grid. And given the pseudo pin and the real pin, and also some of the blockages, we would like to predict some route guide, and where the route guide will be used in the router to affect their routing. Okay, so here our router is a commonly used A-star search using maze routing, and then we hope to use this AI generated route guide to help to do the routing. So we use a strategy, which is the next scale strategy, which is trying to predict the route guide in a higher and higher resolution until it can be something more concrete, concise. So this is our modeling. So you can see we are from a very rough routing map. We want to predict a more concise, more and more concise routing map. And then every time we have a negotiation module that can take in input from other nets. That is the reason why the routing of one net will also consider the routing of the other net. And we are using a transformer model. And at the end, we will combine all the prediction at different scale to give the route guide. Okay. And then the route guide will be used in the costs of the maze routing. Okay, so you can see that if a position is within the route guide, it will have a cost which is smaller than 1. Otherwise, it will have a cost of 1. So this is to encourage the router to use to route according to the route guide. Okay, but it is not a strict restriction. It's just like encourage the router to follow the route guide. Okay, so here are some of the results. We also divide the scenario into multiple complexity depending on number of net we are routing simultaneously. And then you can see a different iteration if we compare with the popular A-star search. This is without guide, this is with guide. You can see that the number of violation and the total wire length is improving. Right? This one 39, this is 35. Okay, right at the beginning, we already have less violation for all the cases. And then when we proceed, iteration 10, this one is 18, 13, and then iteration 100, this one is 11, and this one is 7. So we can see the dropping of the violations consistently for all the cases. And then for the large case, basically the one with route guide can reach a smaller value than the one without. Okay, so that's all I want to share with you today. And there are still a lot of things to be done. For example, handling other design rules, handling larger routing region, more nets, and investigating scalability of the large models development, and also applying to real detail routing environment. These are all the things that we want to do. Okay, thank you.